So, welcome everyone. Welcome to Code as a Crime Scene. Can you hear me there in the back of the room? Perfect. So, today I want to give you a different perspective on your code base. I'm here to investigate the traces we all leave behind as we create our systems. And you will see that there's a lot of valuable information in those traces. And it's information that we can use to detect the code that's hard to maintain, the code that risks to become a team productivity bottleneck, and the code that's most prone to defects. So let's jump right in and talk about what we programmers actually do. We programmers, we don't write code. I mean, sure, we do that as well. But it turns out that that's not where we spend the most of our time. If you look at the research, you will see that the majority of our time is consumed by making modifications to existing programs. And the majority of that time is spent trying to understand what the code does in the first place. So the takeaway here is that if we want to optimize any aspect of software development, we should optimize for ease of understanding. And this is a hard problem. Let's see why. Have a look at this visualization here. It presents a fairly typical system, right? Which parts are hard to maintain? Where will the bugs be? Well, without more context, we just cannot tell. And this is a problem that gets harder with scale, because today's projects are developed by multiple programmers organized in multiple teams. And that leaves everyone with their own view of how the system looks. No one has a holistic picture. And we have actually had this problem for quite a while in the software industry, for decades. So before we move on, I would like to revisit some of the classic approaches to tackle those problems. And then we'll see the limitations of those and move on to new adventures. So the first thing I want to look into is complexity metrics. If we want to know where the complexity is in our code base, why don't we just throw a tool at it, let it calculate some metrics for us, and point us to those locations? And what you see here is just one example of a complexity metrics. This is McCabe's cyclomatic complexity. And it's a fairly well-known metric. So how many of you have been using McCabe's cyclomatic complexity? I see a few hands. So McCabe, it's actually quite simple. What you do with cyclomatic complexity is that you consider your program or your function as a graph. And then you just calculate the number of possible paths through it, right? And sum up that number, and that leaves you with the complexity metric. And the higher that number, the more complicated that code. And I would say that cyclomatic complexity, it kind of makes sense, because it relates to one of the most significant bottlenecks we have in programming, our brain, our working memory. There's really just so much we can hold in our head at once. So McCabe definitely makes sense. But that's really just one example of a metric. We have other things like different coupling measures. And I would like to show a few of them to you here really fast. First we have is something called afferent coupling. How many different modules depend upon me as a module? Then we have afferent coupling, which is basically how many modules do I depend upon? And I would claim that these metrics, they make sense as well. Because afferent coupling, that's basically the cost of changing me as a module, right? And afferent coupling, that's basically the risk that I, as a module, will have to change. So I would say that coupling metrics make sense as well. So why don't we use them? Well, I know why I don't use them. I don't use complexity metrics because complexity metrics are pretty bad at measuring complexity. It's a bold statement, so please allow me to support it with a quote here. Syntactic complexity metrics cannot capture the whole picture of software complexity. And the interesting thing with that quote is that it is from a research paper. And what researchers did was they took a bunch of different metrics. Cyclomatic complexity was just one of them. And then they watched how well they performed in reality on real-world systems. And what they found out was that as soon as they start to control for a number of lines of code, those more elaborate metrics, they didn't add any further predictive value. Wow, the number of lines of code, that's a really rough metric. Is that the best we can do? Please let me read another quote for you. And I actually like this one because it's a little bit evil. The use of metrics to manage software projects has not even reached a state of infancy. And this quote is from Robert Glass. And what Robert Glass means is basically that software is so complicated that we will never be able to measure it. So instead, we should rely upon our intuition. Now, as some of you may know, I have a parallel career as well. I have a parallel career within psychology. And as a psychologist, you just have to love the concept of intuition because it's such a warm, fluffy human subject, right? But what is intuition actually? Well, let me tell you, over the years, as you have worked with software, you have all built up a certain level of expertise, right? You have a lot of knowledge that's stored away in your head. And now, intuition, that's basically just something in the situation, perhaps something you see in a code editor or in your IDE, something that you see that triggers a recall of some of that information that you've stored away. But of course, there's a twist to it. Intuition is an unconscious process. That means you have no control over what kind of information that gets retrieved. And that's kind of what gives intuition this magical quality, right? But it also means that intuition, just like any other unconscious process, it's quite prone to social and cognitive biases. And even if you could somehow control for those biases, which we really can't, but if there was a way to do that, intuition would still not do the trick. And here's why. Because let me tell you, no matter how good we are as developers, there's really no way that our expertise is going to scale across hundreds of thousands or even million lines of code. Intuition doesn't scale. And this is why I suggest that we look into a radically different field, a different discipline that faces much the same open-ended, complex questions as we do. So, welcome to forensic psychology. You probably all know a little bit about forensics. I mean, perhaps you have seen CSI, or you have read about offender profiling in the media. And I also bet that you have all seen the movie Silence of the Lambs. How many have seen Silence of the Lambs? Come on. Oh, cool, most of you. I also bet that you all agree with me that Hannibal Lecter is the coolest character. Right? Yeah. The first time I saw Silence of the Lambs, I was quite influenced by Hannibal Lecter. And I really don't mean that in a scary way, no. I was influenced by forensic skills, not the other stuff. So it's completely safe to have dinner with me. But if you think about it for a moment, it's actually quite fascinating what Hannibal Lecter does. Because Hannibal Lecter, he sits there locked up in his cage, and he receives information from the crime scenes. And based on that information alone, Hannibal Lecter is able to deduce not only the motives, but also the personality of the offender. And first time I saw that, I was like, wow, I want to learn to do that. And then years later, as I started to study criminal psychology, I got terribly disappointed. Because it turned out those techniques that Hannibal Lecter had been using, they have quite a serious limitation. They only work in Hollywood movies. But fortunately, we got some more scientific methods that we can use. So please allow me to give you a 2-minute introduction to geographical offender profiling, and then we'll see how all that applies to code. Now, geographical offender profiling, it's based on a very fundamental fact, and it's also a bit surprising, perhaps because it's so obvious. But geographical offender profiling is based on the fact that offenders, most of the time, they behave just like us. They go to the movies, they visit friends, they go to restaurants, and perhaps they even pick up the kids from school. And as they move around in an area, that's where they spot an opportunity for crime. Because for crime to occur, there has to be an overlap in time and space between an offender and a victim, right? And what that means to us is that crime scenes, their geographical locations, are never random. They contain information about the criminal. And that's information that we can use to catch them, to locate their home base. And I would like to show you how that's done. I hope you can see this. It's really not the best resolution on the screen, sorry. But this is 19th century London, the Whitechapel area, not very far from here. And you see those blue dots here? Those are the crime scenes of the Ripper. So how do we do if we want to catch Jack the Ripper? Well, in geographical offender profiling, what you do is basically you consider each crime scene a center of gravity, right? And then you weigh them all together, but with one important psychological twist. Geographically, all distances aren't equal, so crime scenes that are closer to each other get assigned more weight. And now when we take those crime scenes and weigh them all together, that leaves us with a new center of gravity. And you can see that here in this red spot here in the middle. That's our hotspot. And according to the research, there's a 70% chance that our offender will have his home base there. So if you want to catch the Ripper, that's the area you have to focus on. And we're soon going to see how this applies to software. But before we go there, do you want to know if this offender profiling stuff works? Because, I mean, Jack the Ripper, it's such a simple case study to do because he was never caught. So I could tell you anything. But I don't want to do that. So what I want to do is to take a look at the main suspects in the case and see how well they fit the profile. So let's start with my number one suspect, Mr. James Maybrick. Mr. James Maybrick was a Liverpool cotton merchant, and he used to go to London to do business. And when he did that, he used to rent a room in Middlesex Street. So let's have a look at Middlesex Street on the map. It's there, right in the middle of the hotspot. So James Maybrick is a pretty good fit for this profile. And if you read the news last fall, you probably noticed this supposed DNA evidence against another Ripper suspect, the hairdresser Aaron Kosminski. Now, Kosminski, he probably lived at Sion Square. So let's have a look at Sion Square. As you see, Sion Square is a little bit east of the hotspot. So Kosminski is not as good as a fit as Maybrick for this profile. But that just really highlights an important aspect of geographical offender profiling. A geographical offender profile never points to a precise position. What a profile does is basically that it projects a probability surface onto the geography. And that's important because when I started to learn about this stuff, I was like, wow, what if we could do the same for software? Think about it for a minute. What if we could take those large, complicated systems that we have and narrow them down to much, much smaller parts, just as we did here? What if we could identify hotspots in our software systems? Hotspots where we could now focus our precious human expertise and intuition. That would be a huge win. So how could we do that? How can we use this in code? Well, the first thing we need is a geography of code. And here's my favorite approach to that. Welcome to Code City. In Code City, software systems are visualized as towns. And each building, each class in your system is visualized as a building. And the more complicated the code, the larger that building. And what I like with Code City is that it gives me a pretty easy way to spot the most complicated areas. So you see a large building like that. And if this was all the information I had, and I want to know which parts are hard to understand, and I want to improve the system, I would go after those large buildings, like here, or maybe here. But I would claim that this information is incomplete. And it's incomplete because, let me tell you this about complexity. Complexity is only a problem when we need to deal with it. What if those large buildings, what if they represent code that's been stable for 5 years, that works perfectly in production, that's well tested, that we never need to touch? Well, perhaps we still want to improve it, but we probably have much more urgent matters to attend to. So where are those? To find out, we need to add the missing dimension. Just as we did when we tried to catch the Ripper, we need to know the spatial movement In this case, not of criminals, but of programmers. Where do we find that data? Well, let me tell you, you already have it. We're just not used to think about it that way. I'm talking about our version control systems, of course. So have a look at this. Can you read it from the back? Perfect. So this is a sample from Git. And you see that the version control system, this is a single commit, but we see which programmer made a change, when the change was done, and most importantly, where in the code did the change took place. And this data here, that's a single commit for one single programmer. A large system has virtually thousands of commits. So what if we take all that data, aggregate it, and project it onto our geography of code? Let's see how that looks. So we have our geography, and we project the spatial movement. You see those red spots glowing up there? Those are our hotspots. And the hotspot in this case is defined as an overlap between complicated code that we also need to work with often. So we know that hotspots, they work for offender profiling. But how well do they perform on software systems? To find out, I decided to do a small case study. And this case study was done on a well-known open source project, fairly large system, 400,000 lines of code. It had 89 developers working on it. And I analyzed a period of 1.5 years. And during this time, these developers made a lot of changes. So let's have a look at the profile. Here it is. And if you look at it, you will see that it pretty much looks like an alien, right? But besides that, you will see that I moved back to two-dimensional representation. And the only reason for that is because I think it gives me a much better overview of a large system. And it's a bit hard to see in this resolution here, but it's also a bit more reminiscent of the real-world geographical offender profiles we did earlier. And still, we can spot a bunch of hotspots in here. Now, remember, a hotspot, that's complicated code that we need to work with often. What kind of code is that? What can we expect to find if we look into a hotspot? To answer that question, I decided to mine some different data. I decided to look at the bug distribution in the system. Because bugs have this interesting property that bugs are never evenly distributed in software systems. Bugs tend to cluster. So what I did was, I found out about the distribution of bugs, and then I compared it against the hotspots. And it turned out that the hotspots identified 7 out of the 8 most defect-dense modules. And even more interestingly, the hotspots only made up 4% of the code, yet that code was responsible for 72% of all defects. Or put another way, in this case, if you improve just 4% of the code base, you get rid of the majority of your defects. And the hotspot, the beauty of a hotspot analysis is that it points you to exactly those 4% that matter. So, with a hotspot analysis, we were able to identify the code that really matters for maintenance and the code that's most prone to defects. And that's a very good starting point, but we can do so much more with this data. So let's have a look at that. And let's do that by returning to Jack the Ripper. So the geographical offender profile that we did on the Ripper, it's based on a simple assumption. It's based on the assumption that all those crimes, they were committed by the same offender. That's what we use for our reasoning, right? So how do we know that the same offender committed all those crimes? Well, today we have stuff like DNA evidence. And perhaps you may find hard evidence, or you have a witness. But in the absence of those things, what crime investigators tend to do is that they use something called the modus operandi. And that literally means method of operation. So in this case, it's like a criminal signature. So what do we know about Jack the Ripper? Well, he attacked late at night, and he chooses a particular group of victims. He used a sharp knife, and so on, right? And all those things together, those are the criminal signature of Jack the Ripper. Those are his modus operandi. But a method of operation, that's not something that's limited to criminals. We all have our method of operation. And every software team has a method of operation. So what's the modus operandi of your software team? Well, I would like to show you a way to get an idea about that. And this is the least scientific part of this presentation. So this is not something I use often, but when I do need it, it's quite useful. So we see another version control log. And this time, I want to focus on something that we tend to ignore. I want you to focus on the commit messages. Because every time I type away a commit message, I give away a little piece of social information. So the commit messages, they contain information about the process we use. They contain information about what kind of changes we do to a system. And they also contain information about what features we're working on. So a really, really simple thing is to just pick all commit messages, throw them into a word cloud, and see what comes out. Here's an example. What you want to see is words from your domain, right? What you tend to see is something entirely different. In this case, we see that this team, they seem pretty obsessed by adding stuff. They also seem to spend a lot of time fixing stuff. There may be a correlation, I don't know. But as I said, this is not something I use often. I use that to stimulate team discussions. Just gather the team, show the word cloud, and watch a discussion starting. So it's a useful technique in those rare circumstances. But we can do more to uncover the modus operandi of our team, and in fact, our whole development organization. And one of those techniques is something called code churn. So code churn has received some popularity over the last years. So is anyone familiar with code churn? Some of you, 3, 4? Oh, great. So code churn is basically, again, it's something that's measured from your version control data. And code churn is basically the rate of change in your system. So here's how it looks. Here you just see the diff between 2 revisions. And you see that we have removed 3 lines of code. That gives us a negative code churn of 3. And then we have added 1 new line of code. So that makes our positive code churn 1, right? And the interesting thing with code churn, that's never their absolute numbers. Those are really just numbers. The interesting thing with code churn is the trend. So I would like to show you a number of typical churn patterns. And those are churn patterns that you can pretty much expect to find in most software projects. The first one is this. Again, the numbers aren't that interesting. We just look at a pattern here. So you see the blue line here at the top? That's the total amount of code in the system over time. And the red line here at the bottom, that's the code churn. That's the amount of change in the system. And this pattern shows a good trend. Because it turns out, as we approach completion, somewhere over here, our churn is declining. And that basically means that our system becomes more and more stable over time. We're changing less and less code as we go along. It's a good thing. But sometimes with code churn, you can find some, how should I put it, some interesting patterns. Here's one of them. This is my favorite. It's called the camel churn pattern. And it's called that way because look at this trend. And the first time I saw it, I was quite confused. I mean, what's going on here? Look at that pattern. Basically, we have no activity at all. Nothing's happening. And then we get a huge spike of activity. And then again, nothing happens. And then we get another spike. And nothing happens. And then another spike, and so on. So the first time I saw that, I was really trying to figure out what's going on here. The first thing I noticed was that there was always a fixed amount of time between those spikes. It was always exactly 2 weeks. Aha, the team, they were doing iterative development in 2 weeks iterations. Interesting. So what's happening every second week? Well, they had a demo. And a demo, that's basically like a deadline, right? And a deadline do tend to bring out the worst in people. So what happened was, these developers, they started out planning each iteration, get together, and each developer got assigned a feature and branched away and churned along on a feature branch. And then 2 weeks later, oops, demo ahead, and everyone wanted to have their feature demonstrated. So there was a burst of activity that day to get everything together. Now, there are several problems with that approach. The first one is that it's quite unlikely that every single feature takes exactly 2 weeks. So some of the features were probably rushed to completion. And even if the code was well tested in isolation, there's really no way to tell how well it will play with other stuff. And that puts you at risk for unexpected feature interactions, which are kind of the worst bugs you can have. So if you see a pattern like that, what you want to do is to even out the commits and get a much more predictable stream of delivery. Really, your code base will thank you for that. The final pattern I want to show you is a place where you don't want to be. This is called a def churn pattern. And what's happening here is that if you witness the trend, you see that as we approach a deadline over here, our code churn increases. We're changing more and more of the system. Why is that a bad thing? It's a bad thing because code churn is actually a well-researched topic. And it turns out that code churn is one of the best predictors of post-release defects. So the higher the change rate within a component, the more post-release defects you can expect. So if you see a pattern like that, and you have a deadline over here, you know one thing. You will not be done. You have a lot more work to do before you can stabilize the system. So code churn, that's pretty much like visualizing your process, the real process, not the one you have on paper. All right. So far, we talked pretty much about the design process. But now I want to talk about a different aspect. And it's an often overlooked aspect of software development. And it's an aspect that affects us all. And it's an aspect that frequently leads to projects running late and projects delivering with much lower quality than necessary. I'm talking about the intersection between people and technology, how we affect our code and the other way around. And the basic idea here is that software development is a social activity. And given that statement, I find it quite ironic that the common stereotype of a programmer is as some lone, shy introvert hidden away in the dusty corners of some large corporation. It's just not correct. We developers have a large social component to our daily work. And if you want to witness that, here's a small experiment for you. The next time you see a code review going on, enter that room and start to criticize someone's code. And I promise you, you get to see a range of emotional responses. And it's a range of emotions that will make Robot De Niro jealous, I promise you. And that, my friends, is social activity happening right there. It's also the reason that we get advice like this. You are not your code. And this is actually pretty old. It goes all the way back to psychology of programming, Gerald Weinberg and that stuff. And given this context of code reviews, I actually like that. Because it's a nice way to think about what you do. It's a nice mental mindset to have that allows you to detach yourself from your creations and be able to receive constructive criticism. The problem I have with that statement is that it's not entirely correct. There's a bug in it. So please let me fix it for you. Here we go. Oh, much better. And it's my firm belief that if we want to truly improve, we need to embrace that. And it's my job during the rest of this presentation to convince you about it. And it all starts with you. So let's find out who you are. How many of you are developers? Most of you, cool. Any architects? 1, 2, 3, 4, 5? Any managers? Oh, great, welcome. So, we're engineers, we're developers, we're architects, we're managers. And as such, we probably like to view ourselves as rational human beings. But guess what? Reality tends to disagree. Quite often, we people, we behave in ways without knowing why. We do things without understanding why we do them. And I would like to demonstrate that to you by taking you all the way back to the 70s, to a classic experiment in social psychology. Now, this experiment was quite interesting. What researchers did was they used a young, attractive woman as a confederate. And that woman, she positioned herself next to one of two bridges. The first bridge was something like that, a suspension bridge, a fear-arousing suspension bridge. And that woman, what she did was, she approached every man that crossed that bridge and asked them to do a survey. Now, the survey itself wasn't that interesting. It was really just a cover story for the real experiment that happened afterwards. After the men that crossed that bridge had completed the survey, the woman said to them that, you know, if you have any follow-up questions, why don't you just give me a call afterwards? Here's my phone number. And she gave away her phone number. Then she repeated exactly the same procedure, but this time she positioned herself next to another bridge. And this second bridge, it was nothing fear-arousing about that one. It was a pretty boring, simple walking bridge. So she did exactly the same thing. She approached every man that crossed the bridge, asked them to do the survey, and gave away her phone number. Do you think it was a difference in the behavior between these two groups of men? Oh yes, it was all the difference. It turned out the men in the first group, the ones that had crossed that bridge, they were much more likely to give her a call afterwards. And why is that? Well, think about it for a moment. Say that you are about to cross that bridge. I mean, you will probably not be afraid, but you probably will feel a little bit uneasy. Because, I mean, look, it's deep down there. If we fall down, bad things are going to happen, right? So you walk across that bridge, feel a little bit uneasy, and perhaps you're not even consciously aware of it. And what happened to the men was that biologically, fear and attraction are pretty similar reactions. So when they saw the young, attractive woman, they attributed her emotional state to her. They fall for a bias called misattribution. Now, why am I telling you this? What's the takeaway? Is it that all men are stupid? It could be, but it's not. It's not. I'm telling you this because it has nothing to do with bridges, love, or psychology. This is a common bias that affects us all, men and women, and it happens to us all the time. And the takeaway is that reality, that's really just something that happens in our head. And this bias of misattribution, it can affect you in your daily work. And again, it has nothing to do with love or bridges. It could just be that you have a particular conversation just before you enter a meeting. Or you read a technical blog post before making a technical decision. Or